Hello again, everybody. Welcome to a new screencast lecture. Tonight's topic is one of my favorites, conservation of mass. Let's get started. Okay, the overall content statement that covers this material. Changes of state are explained by a model of matter composed of atoms and or molecules that are in motion. Sounds like the particle theory. A learning target for this material. Students should understand that mass is conserved when substances undergo changes in state and form. What is the main question that we're going to be dealing with in this lecture? What happens to the amount of matter, or mass, during a physical or a chemical change? So in other words, if we start with a certain amount of matter at the beginning of the experiment, what happens to the amount of matter at the end of the experiment? Let's think about a real common chemical change, burning. Here's a neat clip. Okay, let's think about a hypothetical scenario. So let's say we start with 100 pounds of firewood. After we burn all of that firewood, do we end up with 100 pounds of ash? No, it's definitely not going to be 100 pounds of ash. It'll definitely be a lot less. Let's say we end up with 2 pounds of ash. What happened to the other 98 pounds of matter? Was it destroyed? Where did it go? Well, here we see firewood, and firewood is a form of chemical potential energy. When we react it in air with oxygen and it ignites and it burns, it's going to release thermal energy, and it's also going to release things like smoke, water vapor, and then ash, things like that left over. And the end up result is, in your fireplace or in your wood stove, or maybe in your campfire, you're left with a bunch of ash. So if we have 2 pounds of ash, there must have been 98 pounds of smoke and gas that escaped from the system. So where does that 98 pounds of smoke and gas go? Well, if you have a fireplace, it hopefully should go up your chimney. If the chimney catches on fire or is plugged up, you get something that looks like this. Not good. So what is the difference between an open system and a closed system? This is a pretty important concept. An open system is defined as a system in which mass is allowed to leave and to enter. So this jar of jelly beans are allowed to fall out. You can pick up other jelly beans and add it to the jar. The jar is wide open. A beehive would be an open system. The bees can come and go. Here's a clip of an open system, burning pumpkins.
We put a fire in my pumpkin. I made a Minecraft creeper, and it's awesome. Oh no! Did you get that?
Yeah, I think so.
It fell in. Hopefully it stops.
Hopefully.
Before it catches fire.
I don't think it'll catch on fire.
Dad! The pumpkins catch on fire!
A regular coffee mug. You can see that there is steam exiting the system, escaping the system. A tea kettle. You can see the steam exiting the system. Now a closed system would be like if we had that jelly bean jar and we sealed it tight. Mass is not allowed to leave. Mass is not allowed to enter. So the jelly beans can't get in, more jelly beans can't get out. A thermos is a great example of a closed system. If you've ever used a thermos, like you in the morning, maybe you'll put hot soup in it, and the soup will still be hot for you when you eat your lunch. And vice versa for cold beverages. Put a cold beverage in the morning, and it's still cold even in the evening. Here's a clip about Yeti Cups.
Welcome back to What's Inside. I'm Lincoln, this is Dan, and today we're going to cut open some Yeti Cups.
Keeps your drink as cold as science allows, is what this one says. This one makes some pretty strong claims on it. They both say they're 18 by 8 stainless steel construction, and they both say no sweat exterior. So this is kind of a knockoff, I'm guessing. This is the Mighty Mug, the unspillable cup, many people call it. The one that you put down and it won't do anything, and you lift it up. And then I picked up the cheapest one that I could find at the local store.
The cheapest one.
This one was like $8. 16 ounce, 16 ounce, 20 ounce, and then these two are the 30 ouncers.
We're going to put ice cold water in all 5 of these, and then we're going to stick it in the oven and test the temperatures and see what one holds the best.
Each one of them has water in it. Yes, the 30 ouncers don't have that much in it, but it's the same amount as these mugs. That's around the same, 43 and 6. What about this guy? So they're all around the same, but it's dangerous. You could burn your house down, you really could. Let the competition begin. Yes! 325 degrees. We're about 4 minutes into this test, and I don't smell any plastic burning or melting. That's good. Okay, we got a problem. The unspillable mug just fell over. Out of all the mugs. Oh boy. Oh boy. Oh boy. The lid for the Arctic, check it out. It sunk, it melted and sunk down into it. The two Yetis are still pretty good on there. We only went 20 minutes, but I think at 325 degrees convection bake, this is a good enough gauge.
Wait, Lincoln.
Okay, Lincoln. This is the Yeti. Whoa. That is impressive. I can see 4 ice cubes and 1 piece of a fifth, and the water is at 39 degrees or 3 degrees Celsius. Does the Yeti cooler work? Look at this, 16 ounce compared to this 16 ounce. 3 degrees on that one Celsius. This one instantly jumps 13, 14, 15, 16, 9 degrees Celsius, 48 degrees Fahrenheit. What did we learn today?
That Yeti cups are very good at keeping water cold.
They do their job. I don't know, I'm a believer. I'm a believer of the Yetis. After our little, not very scientific test, I'm a believer. But, let's cut them open now and see what the inside looks like. We got the bottom off. Good, but this is some tough metal. Just made a noise, like some gas came out of it. But the Yeti is tough.
Whoa!
Look at the layers. So there's a thick layer of metal, air in between made that loud hissing noise once I hit it the right spot with the hatchet. And then the very bottom of it, it has a lot of space in the bottom. That's pretty well built for a cup to drink ice cold beverages.
Here is the largest attempt at a closed system. It was called Biosphere II, and this is at the University of Arizona. The idea behind this is to replicate Earth in terms of, like, if you go traveling out in space, having to make a new space colony out on another planet that doesn't have a proper atmosphere. That was the idea behind this. It's pretty neat. Here you can see the different biomes. They have savanna, ocean, desert, rainforest. Here's a look at the ocean and the rainforest. The windows up above.
Since the dawn of humanity, we've had a complex relationship with nature. We're obviously a part of it, but often we view ourselves as separate from nature, or even working against it. Through the control of fire, the rise of agriculture, and the growth of our civilization, we've been molding the Earth's environment to suit our needs.
We try to control it, we try to protect it, we depend upon it, and we try to understand it. But could we recreate it? Taking what we know about the planet and what we need to survive, could we replicate the Earth's ecosystems?
Well, back in the late 1980s, a group of scientists attempted to do just that. This cool-looking giant greenhouse building is known as Biosphere II.
Okay, but where's Biosphere 1?
That's a great question. It's one that we're commonly asked. So, Biosphere 1 is the Earth.
This is John Adams, Deputy Director of Biosphere II, which is currently owned and operated by the University of Arizona.
Biosphere 2 was really thought up in the early 80s with this notion that there was a lot of discussions about space travel, extended stays in space, and the recognition was how are you going to do that? Inevitably, you would have to take some of these biological processes that we're so dependent here on Earth for into space and balance what happens between them to support the existence of a certain number of people for an extended period of time. No one really had tested that on a large scale.
And Space Biosphere Ventures would attempt that. They intended Biosphere 2 to be a completely closed, self-sufficient system, like the Earth's own biosphere, where plants, animals, and humans could live indefinitely. In fact, it was the largest closed system ever constructed and one of the most ambitious and complex Earth science experiments ever conceived.
And for the most part, they got it right.
In September of 1991, 8 people were sealed in Biosphere 2. Known as Biospherians, they would live inside the structure for a full 2 years. All their food, water, and amenities had to be obtained from the habitats inside the biosphere. They were to have no direct contact with the outside world for the entire length of their stay. And almost right away, things started to go wrong on Biosphere 2.
And one of the first things they began to notice is that oxygen began to go down and down and down. About halfway through this first 2-year mission, it got so low that they had to add oxygen in because they were concerned for the safety of the individuals inside.
Along with the oxygen loss, Biosphere 2 experienced a number of other problems, including massive plant and animal die-offs. The Biospherians had difficulty raising enough food to feed themselves and were constantly hungry. This contributed to morale problems, causing a rift in the group, splitting them into 2 factions.
A lot of people like to say because of sort of this initial falling out and loss of credibility that it was a failure. And no experiment is a failure. And that's what this was and is it's an experiment on a grand scale, had never been attempted before, and the engineering is absolutely amazing. But what they did learn, and probably, in my opinion, the single most important lesson, is really how little we truly understand Earth systems.
Biosphere II was designed to contain 5 biomes or habitats: a rainforest, an ocean, a savanna, a mangrove wetland, and a fog desert, along with an agricultural area and living quarters. Although people don't live in the biosphere anymore, the ecosystems are still thriving and have been growing for over 20 years now.
So we're walking through what we call the lowland of the rainforest, and you know, the rainforest is a pretty cool area. I mean, if you can believe it, we're standing in southern Arizona, but look where we're standing.
Yeah, it's amazing.
So all of this growth that you see, you know, has taken place over the past 23 years that this system has been growing and establishing.
It looks like you're running out of room. The trees are hitting the ceiling now.
Oh, they are. And you know, one of the things we periodically have to do is we have to go in and trim those upper canopy trees. Now, I think the most important thing for people to remember is that you can never recreate Earth in its entirety. It's impossible. There's just too many complex things. Really?
Dang it. Let's get out of here, guys. No.
But what you have now is you have plants that have been growing for about 23 years. You have a soil column that's confined and isolated from the outside world. So underneath all of Biosphere is a big stainless steel liner. So there's no exchange or interaction with desert soil outside. So all of this is evolving and able to grow inside of this system with very little influence from the outside.
Oh yeah, it's warmer.
So you can feel, I mean, almost an instant humidity change.
Yeah. Oh yeah, the fogged up camera lens.
So every rainforest has to have a waterfall and a pool of water, and we'll walk down and we'll see our stream.
Okay, cool.
So this is our ocean.
We going swimming?
We are. You ready to go scuba diving? The tank itself is about 1 million gallons. By the time you put in the rock and the sand and everything else, the volume of water is just under 700,000 gallons.
Cool. Seems like it smells like a beach. We're on the beach.
It's pretty nice here. I mean,
It is.
what a huge change from sweating in the rainforest and the humidity to something that's pretty cool.
This feels like a perfect day. Like it's nice and cool, not too hot, on the beach. It's great. In beakers and small lab setups.
Not always a great model for something as massive and complex as the Earth.
And the only way to test Earth systems is to use the Earth itself.
But that must be pretty hard, if not impossible, to control all the variables.
But Biosphere is this intermediate step where you have these established biological communities, and you can come in and say, hey, I want to increase the temperature and look at how the system behaves, or I want to cause a drought, or I want to change the atmospheric concentration, whether it's CO2 or some other gas, and look at collectively how this whole system responds. And there's no other place in the world at this scale that you can do those types of experiments.
Some of the earliest research at Biosphere focused on manipulating CO2 levels in the atmosphere.
To model projected CO2 levels in our own atmosphere and see what happens.
So we've heard about carbon dioxide going up in the atmosphere, and we hear a lot of the debates centering around how that's going to change the temperature of the Earth. But one thing we know for sure is that as you increase atmospheric CO2, it's a gas that's soluble in water, and what ends up happening as it diffuses into the water, it begins to lower the pH.
This is called ocean acidification.
Since coral reefs provide a habitat for a quarter of all marine species on the planet.
How can we take what we learned in Biosphere and potentially create bioregenerative life support systems? Biosphere was extremely ambitious, and they tried to put in as much diversity and all of those natural systems that you find outside. Well, they quickly learned that it was very difficult to balance all of that. So the next generation, if you want to say, was to go with really a hydroponic setup. What you've got here now is a system that's growing and recycling nutrients, carbon, oxygen in a way that, in theory, could potentially support a person for 1 year.
This is how much would be needed for one person?
Yes. You'd start out with the appropriate amount of water, and then it would just recycle that water. It would eventually be able to recycle, our components to recycle your waste, and to produce enough oxygen as well as caloric intake.
This is just a model, but the idea is that eventually a lunar greenhouse like this would be sufficient to provide all the food, water, and oxygen for one astronaut on a daily basis.
So we really now have a unique opportunity to leverage this one-of-a-kind world's largest earth science laboratory in ways that no one could have even envisioned early on. We only have Earth, and we're dependent on the systems and the processes. And so figuring out a way in which we're able to continue to have those resources and exist in a way that's favorable for us is crucial.
Okay, that brings us to Antoine Lavoisier. You can see the time period he lived. Here's his wife, Marie Anne, and she is pretty well known for not just being his wife, but also being his assistant in terms of his scientific experiments. Another interesting fact is he was about 28 years old, and she was 13 years old when they were married. They conducted an experiment to test if mass is created or destroyed. Here's a schematic of his famous experiment. He had water in an airtight glass container here, labeled A. He had a stove. He lit the stove, heated it up. The water would start to boil. As the water boils, it creates steam. The steam would travel through an iron rifle barrel that he had also placed in a grill. The steam would shoot through the hot rifle barrel and be collected through this curved pipe here, and this would be a cooling vessel. The steam would go through this curved pipe, and as it went through this curved pipe, the steam would cool and condense into liquid water. That liquid water was collected, and he noticed that he ended up with less water than he started with. So, like, for example, he started with a gallon of water here, and he ended up collecting less than a gallon of water over here. He also noticed that the iron rifle barrel started to rust. So it went from iron, Fe, to Fe2O3, which is different. That's rust. He also discovered a gas. A gas was collected, and that gas turned out to be flammable. It was hydrogen. He added up the weight of all of the original ingredients, the water, the rifle barrel, before the experiment, and when the experiment was over, he added up all the weight of the liquid water that he collected, plus the hydrogen gas, plus the weight of the barrel, and he noticed that the weights were exactly the same. Here's a clip dramatizing the experiment.
Gentlemen. Monsieur, it is my great ambition to demonstrate that nature is a closed system, that in any transformation, no amount of matter, no mass, is ever lost, and none is gained. Over here, please. This precise amount of water is heated to steam. This steam is brought into contact with a red-hot iron barrel embedded in the coals. From this end, we cool the steam. But interestingly, we collect less water than we started with. So clearly, we lose a certain amount of water. However, we also collect a gas. And the weight of the iron barrel increases. Now, when we combine these two increases, the new weight of the iron barrel and the gas we have collected, they are exactly equal to the weight of the lost water.
Ah, but is it atmospheric air, Monsieur Lavoisier?
No. No, because I am measuring it to the very last grain. I can see that it is lighter than the air around us, and moreover, it is flammable. Voila.
Water is made out of hydrogen and oxygen. So what he had done is get the oxygen to stick to the inside of a red-hot iron rifle barrel. He was basically just making rust, which is oxygen and iron, but he was making the rust really quickly. Now that left the hydrogen, what he called combustible air, and that was just floating around as a gas. No mass had been lost, it had merely been transformed. And now, he wanted to transform it all back into water.
This is only the beginning. In the next few months, I hope to demonstrate that I can recombine this combustible air with vital air and transform them both back into water. I will recreate exactly the same amount of water that was lost here in this process. It is my hope to complete the cycle, water into gas, into water, and not a drop lost.
For a long time, Lavoisier had suspected that the exact amount of matter, the mass, involved in any transformation was always conserved. But to prove this, he had to perform thousands of experiments, and he had to do the measurements with incredible accuracy. That's where his great wealth from being a tax collector came in. He could afford to commission the most sensitive instruments ever built. he became obsessed with accuracy.
For years, the Lavoisiers burned, chopped, melted, and boiled every conceivable substance. They'd shown that as long as one is scrupulous about collecting all the vapors, liquids, and powders created in a transformation, then mass is not decreased. Liquids might become gases, metals may rust, wood may become ash and smoke, but matter, the tiny atoms that make up all substances, none of it is ever lost. The crowning glory of this opus was their remarkable use of static electricity to cause oxygen and hydrogen to recombine back into water.
When he put this all together, he called this Lavoisier's law. That stated that the mass of a system must remain constant as mass is not added or removed. Today, that's known as the law of conservation of mass. The mass of a system must remain constant as mass is not added or removed. In a closed system, mass before the reaction is the same as the mass after the reaction. Now, at the very end of that dramatization, you may have kind of heard the ominous music at the end. Think about the time period that he was living in. This was the time of the French Revolution. And Lavoisier, he was a very wealthy man, and the way he got very, very wealthy is that he was a tax collector. And because of that, a lot of people didn't like him, because most people don't like paying taxes. And one of the bad things that happened is he was actually arrested, and unfortunately he was executed during the French Revolution. There was a mathematician, and he remarked at the time of the event that it took them only an instant to cut off the head, and 100 years may not produce another like it. What he was saying is that they destroyed a great scientist, a real genius. Today we know this as the law of conservation of mass. Sometimes it's called the law of conservation of matter. Today we know this as the law of conservation of mass. During a physical or chemical change, the total mass before the change is equal to the total mass after the change. Sometimes people say this as matter cannot be created or destroyed. The matter may end up looking different, but it's still matter. It's just change from one form to another. Well, that's all we have for today. Be sure to check out the music video we have, Conservation of Matter. It's one of my favorites. Hope you had a good one. See ya.